Hey everybody, welcome back to Not So Sirius. My name is Tommy, and as always, I'm joined by Sam, Joe, and Michael. In today's episode, we wanted to talk about the formation of black holes and how they appear in our galaxy, as well as all the scientific possibilities they hold for the future of humanity. As always, if you have any topics that you'd like to see us discuss in a future episode, leave that down below. We'll be more than happy to hit that in a future episode. Without further ado, please enjoy.
So today we're going to talk about black holes, which is it is a very interesting topic, but we should also, as a little disclaimer, note that the four of us have lacking knowledge in black holes, and it's very patchy, and we have far from a complete understanding of how they work and what the science says about them. But I think from our confusion, there something interesting emerges in that this also means that there's lots of very interesting questions that we can be asking and very cool ramifications that come from it. So today we were planning on talking about how black holes form and what they are, and then we're going to discuss the picture that was taken of the black hole by the Event Horizon Telescope last year. And then we're also going to talk about some of the open questions in black hole physics and some of the cool implications of black holes.
So I'd say the first question that comes up in terms of black holes is what exactly is a black hole, and also when did it first come up in terms of our scientific understanding of it.
How do you even get to black hole per se?
Yeah.
Right.
The object.
So I mean, the object itself, well, the idea of a black hole is just an object that gets heavy enough and small enough that the gravity from it is so strong that nothing, even light, can escape from it.
Mm-hmm.
And
Right.
I believe that simple idea of what a black hole is was suggested as early as the 18th century by some people based off the Newtonian picture of what gravity was. But I don't think anyone took it seriously, and there was no observational evidence for it, and this was just more of just some crazy thing that some crazy guy thought of. And I think it took us until the early 20th century to even have a scientific inkling that they exist. And then even then, until I think the early 60s or even maybe the 70s, we still had never confirmed the existence of black holes. And I don't believe that many people spent that much time thinking about them.
Yeah,
Right.
and so in 1915, around then, Einstein proposed his theory of general relativity, and with that, his field equations, basically describing how space-time exists and how there's curvature to space-time.
And how most people think of it is just the fabric of space-time, and how anything with mass, will put a dent in that fabric, and then naturally, as balls do, they gravitate towards the lowest point in that space-time fabric.
Mm-hmm. And also there's not only Einstein, but also another character, Karl Schwarzschild, and he was also a mathematician and physicist. And in 1916, and a few years around there, when he was stationed out on the Eastern and Western fronts during World War I, he still continued his research and he published 3 really important papers that kind of provided solutions to Einstein's general relativity and field equations. And out of that came the idea or the notion of a black hole, even though the word black hole wasn't coined until
1971, I think.
Yeah, something like that.
And I mean, the mathematical description itself is very interesting. But as we were talking about, it's if you picture the fabric of space-time as just being a large piece of fabric that's stretched out, and you take a ball and you make it move on this piece of fabric, it'll kind of sink in and move around. But if you took a ball heavy enough and small enough, it would pierce through the fabric. And at least to my understanding, that's pretty much exactly what a black hole is. It just breaks the fabric of space-time as we know it.
And it should also be mentioned that you don't necessarily need something that's massive enough to be a black hole. Any object with mass can be a black hole. You just need to physically push it down to a small enough radius. And so that radius named after Karl Schwarzschild, is known as the Schwarzschild radius, which is the radius at which an object of any mass will exert enough gravity or light won't escape.
So, for example, if the Earth was squished really hard by someone really huge and really strong into something, into a ball of, I think it's 8 millimeters, then it would itself, then the Earth would become a black hole. Obviously, there's no mechanism for that to happen yet because nothing is squishing Earth. But if that were possible, then anything could become a black hole. I mean, a person, a watch, if it gets squished down to small enough, it can itself become a black hole.
That was for the sun, which is more massive than the Earth, obviously, that would be 3 kilometers. And so 3 kilometers is still very small, astronomically speaking, in terms of an object you want to observe with a telescope. And so that's why also after Einstein and Schwarzschild, people, even though they understood the math somewhat, they didn't think it was physically possible. And the 20th century is defined by not necessarily radio telescopes, but observing things that exert light. And black holes are defined as things that don't not exert light, but give off light or electromagnetic radiation. And so that's why it wasn't, there haven't until recently been able to be observed.
The other thing that I think is cool is that since the dawn of time, people have always been looking at the stars, and even today, that's still what people are doing. But the only mechanism we've had to do that is to look at light or some kind of electromagnetic radiation coming from elsewhere. And so all astronomers from the earliest peoples of the prehistorical times to until like 10 years ago were exclusively using light to find out stuff about the universe, which, considering that the discoveries that we have made are pretty impressive. But now, for example, with LIGO and some of those other big experiments, we now have gravity observatories, which give us kind of a second port of entry into exploring the universe.
And that's not to say that nowadays, when we look for black holes or objects like these, we still can't use light as a measurement, because
that's still primarily the measurement.
It is a big part of being able to detect some of these black holes out there in the universe. Still using light on the disks of black holes, not necessarily inside them, but light can be used as a metric to see where they might be around.
And so historically speaking, it wasn't until the 1960s when Stephen Hawking and another guy named Penrose actually suggested scientific ideas that could show or suggest that black holes were physically possible. And they suggested that, well, if you have a large enough object, it could collapse in on itself through gravity. And that's where the idea of, well, possibly maybe there are massive enough stars out there in our universe, in our galaxy, that could collapse and form a black hole.
Right.
And then it wasn't, go ahead.
Yeah, we should note that, for example, there's no naturally occurring mechanism to squish Earth into a small enough radius such that it would become a black hole. But for some very, very massive objects like stars, for example, there is a way that naturally the star could collapse on itself in such a way that it becomes small
enough.
By
the nature of what stars are, at some point, if they're large enough, they're going to be to collapse on themselves.
Yes. Anyway, I interrupted you, Michael. Go ahead.
Oh, and then I was going to say, so there's a fairly large amount of time between 1915 and 1916 with Einstein and Schwarzschild, and 1960s with Hawking and Penrose. And then after that, it wasn't until the late, I think 1995 or so, that we first, as Sam kind of said, where you can indirectly observe black holes through understanding the light around it, or the stars that move around it. It wasn't until then when a ground-based telescope observed the supermassive black hole, as it's known, at the center of our own Milky Way galaxy, known as Sagittarius A star. And so they observed, obviously a black hole they can't see with their telescope, so it's black there. But they were able to observe stars as they orbited the black hole at the center of the picture. And they were able to see how fast those stars moved, or how quickly they moved, as they passed closely by the black hole. And using some simple Newtonian equations, they're able to say, well, if this star is moving this speed around the black hole, or that object at the center of the image, then that object at the center must be of this mass. And that object, the mass of that object turned out to be 4 million solar masses, which a star is not 4 million solar masses unless it's a black hole.
Right.
I mean, yeah, and just to put into context how we observe it, it's kind of like if someone could look at the solar system and could see all of the planets going around in neat circles, but somehow the sun was invisible, you would think, there must be something in the middle that I can't
Right.
see, but that's still making all of these planets turn around it.
Right. And the big question is obviously there's no stars that are 4 million solar masses. And I know Sam did a lot of like background on this, but that's kind of the big question around supermassive black holes and how they form to become the center of galaxies.
Yeah,
My
and I
apologies.
mean, I looked into a little bit of it, and it's still theorized. I don't think people know exactly. I don't think we may ever know exactly, just because it's not like we can get into actually looking at these things close up and analyzing all their characteristics. However, I believe it is generally accepted among scientists, where they assume that these supermassive black holes, these very large ones that are sitting at the center of galaxies, are formed in the midst of other galaxies forming in the universe, which is why they're seen at the center and why they're like the root or like the point at which these galaxies orbit around. And so, yeah, I mean, that's basically where they form. And then obviously, I know Michael looked into more of the stellar formation of black holes, where you get from a star, which is what we might see more commonly in the universe, as opposed to some of these supermassive black holes. And so, if you want to go ahead and share a little.
Sure. Well, so the nearest supermassive black hole, as I mentioned, is the center of our own galaxy, so about 23,000 light years away from us here on Earth, so very far away. And I believe that there are stellar black holes that are closer than that distance. And so basically, a star that's massive enough at some point in its lifetime will collapse on its own and kind of die in what's known as a supernova. So it'll basically explode and leave behind sometimes a neutron star or a black hole.
Right. And that's based on, stars are massive enough to determine whether or not they're going to turn into a neutron star or black hole. But the only reason that they have the outward pressure to not collapse on themselves immediately is the nuclear fusion that happens within the core that, you'd learn about in elementary or high school. And so as soon as that process, like those processes run out, gravity overcomes all of that outward pressure, and then you get the end results of stellar evolution.
Mm-hmm. And so for a star like our own sun, which is 1 solar mass, it'll not end up as a black hole or explode with a supernova. Instead, it'll end up as a white dwarf. But say you combine 8 of our suns, so you have a star that's 8 solar masses. Well, that's large enough to then collapse into a black hole. But a stellar black hole, not a supermassive black hole.
Right.
And just to go back to what the white dwarf is, so when our sun runs out of nuclear fusion to take, when our sun can no longer do its own nuclear fusion to keep itself up, as it starts collapsing, another mechanism called electron degeneracy that starts to happen. And that then takes over the role of producing the outward pressure, and the electron degeneracy then is what keeps up a white dwarf.
Right.
But then, if the object there's this thing called the Chandrasekhar limit, which is 1.44 solar masses, which says that any star that's heavier than 1.44 solar masses cannot be held up by electron degeneracy. So it means that anything that's heavier than 1.44 solar masses will go on to collapse further than a white dwarf.
And this is just to clarify for you, it's like these stars that you're saying for the Chandrasekhar limit are for white dwarfs.
Right. Anything heavier than the 1.44 solar masses
that turns into a neutron star.
That will then turn into a neutron star.
Right, and it's held up by, instead of electron degeneracy, it's held up by neutron degeneracy. That's the name, neutron stars.
Yeah. Yeah. And if the star then is still too heavy, and it itself cannot be held up by neutron degeneracy, then that's it. It's game over. It will collapse into a black hole.
Right.
And I think also, just to bring up, how we're able to even detect some of these objects, let's say not even the supermassive black holes that we can see at the center of the galaxies, but stellar black holes. There's this thing where black holes are so dense and their gravity is so great that they accrete material around them from other
Mm.
sources that are around them or close to them. If it is in the remnants of a supernova, if it's massive enough, those things, that gas, those materials, will orbit or will be sucked into the black hole per se. And so the mass from those materials can be heated and changed into radiation, which then allows us to be able to see some of these objects. Whereas
Right.
it's not to say that a black hole is lit up per se, but the area around the black hole is lit up, and so we can observe them that way in a sense.
Right.
Right.
Yeah.
I mean,
It's kind of how Saturn works. You know, you have all this material that gets expunged from the supernova, but the black hole is so massive and has enough gravity. Then instead of nice peaceful rings, they turn into hot, scorching, nearly the speed of light rings that we're able to detect very easily.
and instead of it being called a ring, it's called the accretion disk.
Right. Yeah.
Exactly.
Which I believe, and I know we'll go into more detail about this, but the picture of the black hole that was taken last year, I believe you don't actually see the black hole. You just see the accretion disk around the black hole. In the same
Right.
way that in the movie Interstellar, when they go near Gargantua and they have that very cool rendering of what Gargantua looks like,
Mhm.
you're not actually seeing the black hole because you cannot see a black hole. You're just
Right.
seeing the stuff around it and what it does to the stuff around it.
Mhm.
Well, you
Yeah,
see
and-
the shadow of a black.
Interesting effect where light coming from any direction, because the black hole is so massive, it gets sucked in and warped around the black hole, so you don't actually even get to see the event horizon. You get to see a shadow of the event horizon that just happens to be double, I think double, something like that, like double the width. So you don't even get to see the outside of the black hole, let alone the singularity in the middle.
We should touch on what the event horizon is. The event horizon is just it's sort of the point around the black hole at which if an object crosses it, it is forever destined to go inside the black hole and has no means of escaping possible. So it's kind of the border of the black hole. It's the zone,
Right.
it's the final, it's the zone of no return, the point of no return.
Yeah.
Where not even light can escape.
Yeah.
Yep.
Although black holes do evaporate, and so that's through Hawking radiation.
Yeah,
on the
which
side.
is a kind of a crazy.
Yeah,
Crazy
I can
notion.
try to explain it. Essentially, there's spontaneous annihilation of like subatomic particles that happen. I believe it's matter and antimatter, but don't quote me on that one. But regardless, these particles appear and then instantly crash into each other and completely disappear. But when this happens at the border of the event horizon, obviously nothing can escape. So you'll have one particle on the outside and one particle on the inside. The particle on the inside obviously gets sucked straight in and can never escape. So the one on the outside gets shot out with a ton of energy and maybe some mass even. And that loss of energy that gets shot out is Hawking radiation. And that's how over hundreds of trillions and billions of years, a black hole can actually lose all of its mass.
Yeah, and I mean that brings up 2 points. I think the first is that black holes can and do die. So a black hole is not the end forever. I mean, I guess what's in it and what it does is the end forever. However,
As far as we know, yeah.
if you have the luxury of being very far away and looking at it, and you had an infinite amount of time somehow, if you were well endowed at birth, then in that case, then you could see black holes die out because a black hole slowly loses energy through Hawking radiation over time.
Yeah.
And I think the other interesting thing with Hawking radiation is that, so one of the laws of thermodynamics is that entropy always increases in the universe. And I believe that this was why the idea of Hawking radiation was so controversial when it was first put out there, was that if Hawking radiation would somehow reduce the entropy of a black hole, if that were the case. And so I think the solution to that was, as Tommy said, it's this whole idea that that even though Hawking radiation locally reduces entropy, there's a counterpart mechanism to it that I think increases it more.
Yeah.
So I think that's how that problem was resolved by, I assume it was Stephen Hawking.
Mhm.
by,
And
and that I think that was a workaround to the problem that Hawking radiation has a counterpart mechanism as well.
right, and I know we talked about both supermassive and stellar black holes, but there's actually four types of black holes. Like an intermediate black hole, which I assume would be something between like less than a solar mass. So imagine if you collapse the Earth into itself, that'd be classified as an intermediate black hole. But there's also miniature black holes, and I know back when CERN first started, people were concerned that it would create a black hole and that it would just suck the entire Earth in it, destroy the entire world. But actually, Hawking radiation just evaporated it nearly instantly, and so nothing ever happened. So we know that, yeah. So we know that these events like can happen, just on a much slower scale for much bigger black holes.
Also, a little side note right now. I think a cool thing that I learned about a couple months ago is that if you apparently take two protons and two protons, and you collide them together for a very, very brief instant, you have this whole soup of quarks and antimatter and all of this stuff flying around, and it makes a liquid, which I believe is called a quantum liquid. And apparently the behavior of the quantum liquid is best understood through the mechanisms that we understand black holes operate in, which is an interesting kind of circularity in that black holes are the biggest and the most heaviest things in the universe. And this quantum liquid is one of the smallest things that we have. And it's an interesting circular. And I learned about that by watching something on the internet with Alan Adams, who's a lecturer at MIT, who does really, really great, who has really, really great stuff on the internet that's great to learn from. Sorry for the side note.
I mean, I think we've covered a lot of base about what black holes are like and how they formed and what kind of characteristics they have. So I think we can get into the image that was captured, I believe, last year.
Right.
The collection of data took a while, and so they had it in 2017, I believe, and then it took
the final
2
formation,
years
right?
to process through the data, and then they released it in April of 2019.
So should we talk about the way that the picture was taken first before we go into the picture briefly?
Yeah, I think we can talk about the picture as well. I think that'd be good.
Yeah. I think so it's through the Event Horizon Telescope, I believe it's called, but the name is a bit misleading because it should be called the Event Horizon Telescopes or collection of telescopes, because it's not just one telescope, it's multiple across the entire surface of the Earth. Also, they're not your typical, when you think of a telescope, a ground-based telescope with a mirror that takes optical images. Instead, these are all radio telescopes. So you can think of them as giant dishes all across the globe.
And so we observed the picture of the black hole that was taken using in the radio wavelength regime. Mm-hmm. And so that's very, very long wavelengths, which is why the radio telescopes are always huge and have enormous dishes. Mm-hmm. And the problem with the fact that that radio wavelengths is very long is that it's roughly not very information dense. So you need a really, really large telescope to get the same kind of angular resolution that you would get with a much smaller telescope operating at higher wavelength.
Angular resolution just translates to like picture clarity.
How small the angle is that you can see.
Right.
And so the way that this team of researchers got around it was by using different telescopes spread all over the Earth. And as the Earth rotates, the telescopes would move through space, and you would be able to sort of get different like pixels, if you will, of the black hole picture by these different telescopes moving through space with the Earth. And so the reason why, for example, why analyzing the data and making it into a coherent picture took so long was that we needed a lot of very new ways of collecting and putting the data together, just because we had so much missing pieces of it. And it's a very hard task to kind of gather information from different places around space. And I think one of the coolest things is that that the picture that was taken was not just assembled in the same way that we assemble a picture from the different pixels when we use a camera. We had to put we had to they designed algorithms that kind of built on what we expect a black hole to look like. And that, I think that was from what I understand, that was one of the hardest things of, well, the picture can't look like an elephant because there's obviously no elephant in the black hole. But
Right.
so if it's going to tell, if one of the possibilities that it's an elephant, that's obviously not the right possibility. But on the other hand, how do you make sure that your model doesn't exclude too much and doesn't just give you what you were looking for? And so I think that was one of the very challenging things that the Event Horizon Telescope team overcame.
Right, and there's some interesting possibilities based off of that kind of technology, because obviously we used a bunch of different sites that utilize the entire circumference and like volume of the Earth to stitch together this picture. But who's to say then that we can't expand that width further, and place satellites that expand that reach, and even put computational telescopes on the moon or Mars once we get there.
Mm-hmm.
That will increase the size of our radio telescopes, from the size of the Earth to multiple, maybe even 100 times the size of that. That will only increase the clarity of the image.
And then one thing that they're still planning on doing is increasing the number of radio telescopes on the surface of Earth. And so instead of, I don't know how many telescopes were involved, but say there were 10. If they increase the number over the next few years to, say, 20 radio telescopes that observe the black hole, then you don't necessarily have to increase the effective diameter by putting them in orbit around Earth. Instead, you can just increase the resolution that way.
Mm-hmm.
Having more
that's more data that you have and less things that you have to stitch together.
Yes, thank you. I think one other interesting thing to observing black holes is that now that we have those gravitational wave observatories, at the first time that we detected gravitational waves was through two different gravitational waves observatories, one in Louisiana and one in the state of Washington. And so because there were two, based on the timing difference of when the gravitational wave hit the first one and then the next, we had a rough idea of where the gravitational wave event was coming from. But now that there's more and more being built, I know there's one in India, there's one in Italy, and there's one in Japan that are being built. The hope is that we'll be able to pretty accurately pinpoint where the gravitational wave event came from, and hopefully quickly enough that that we would then be able to point all of our telescopes, radio telescopes, all of the telescopes that we have towards where the gravitational wave event is coming from, which would then hopefully teach us which would then provide us a lot of observational opportunities to see how black holes work and interact together.
Like if we're able to use these gravitational wave opportunities to then observe like what the end result of two black holes colliding with each other, that could, give us a lot of useful information.
And so in terms of the actual Event Horizon picture from 2019, so they pointed the telescopes, I believe, at two different supermassive black holes. The first one being the one at the center of our own galaxy, Sagittarius A star, and the other one, which is the image will show it on the screen if you're watching on YouTube, which is the center of M87. I don't know if it has a certain name, but it's the supermassive black hole at the center of M87.
Yeah.
And so you'd think that the one at the center of the Milky Way galaxy would be the best candidate to take an image of, just because it's closer. It's only 23,000 light years away, whereas I believe the other galaxy is 1,500 times further away, I believe, or something like that. It's much further away. But it turns out that the one in M87 is much more massive, and so therefore the event horizon, or the size of the black hole, scales up with the amount of mass it's contained within it. And so it ends up being that M87 is the better picture to take over the one at the center of the Milky Way.
But I believe not by much, right? I think
not by much.
It's bigger, but it's also much further away. And so I think on balance, it's only a little bit better to observe than.
But I believe with the telescopes, the current technology we have, it's probably still a better candidate to go with the best seeing one, just because we don't have the best resources to be able to actually observe all these things. So
Also, I'm certain it's depending on the conditions during the actual observation of the different supermassive black holes, and also what the computer simulation, or like, because as Joe mentioned before, they kind of had to compare different models of their end result image, and so it may have just ended up that the results for M87 just happen to show better structure that they were trying to show in their paper.
Right. And speaking of the structure, the picture does have some interesting characteristics. I know when it first came out, a lot of people were curious as to, why one side of the black hole appeared brighter than the other. And I know there was a lot of things going around, but I think the most agreed upon answer for this is that the accretion disk that we talked about earlier is facing towards the camera. So if we were looking at it dead on, it'd be very flat, almost like 2D. And as it rotates around the black hole, it rotates on the top, it rotates away from us, and on the bottom, it rotates towards us. And so if you've ever had an ambulance drive by and it sounds louder coming towards you and fainter as it goes away, it's the same effect. It's called the Doppler effect. And it works with light as well. So that's why the bottom appears much brighter than the top.
Yeah. And so this here is the picture that in question. And so this is the quote, the accretion disk, which I still don't fully understand in which direction it's pointing, but you can see that the accretion disk goes kind of all around, which is a strange thing because there's a black hole in the way. But I think one of the cool features of the black hole is that what we're seeing in this picture, so I believe this part of the ring, which over the black hole, is actually what's behind the black hole. It's just that the black hole that's in the center of this picture is bending the light around it. And so we actually get to see the light from stuff that's behind the black hole actually gets to us in a process that's called gravitational lensing.
Mm-hmm. Yeah, like the accretion disk is still a disk, but because of the gravity of the black hole and how it can trap light, it's also able to bend light around it. And just based on all the spins going on, the black hole would be spinning so that any light coming towards it, would be bent in the same direction that the accretion disk would be going. So all of the light and the gravitational lensing would, get sent towards us from underwards and get pulled away from us on top.
Did you want to bring up the picture again, Tommy?
Yes.
And so I think another misconception about this image is that people might say, oh, that's the black hole at the center of the accretion disk, that, the darker region, except that's not necessarily true. So it turns out that there's something known as, I believe it's called the Intermost stable orbit, and that's about 3 Schwarzschild radii. So again, a Schwarzschild radius is just the radius at which light can't escape. It's the radius where you find the event horizon, where if you enter, you can't come back out of the black hole. And so all matter in the accretion disk, if it falls within this Intermost stable orbit, it immediately gets sucked into the black hole. And so you're not seeing the black hole as that full dark object. Instead of, it's much smaller than that. So if the Intermost stable orbit is 3 times the Schwarzschild radius, then it's 3 times smaller.
Right. And just because you're inside of that shadow where the innermost stable orbit is, it doesn't mean you automatically get sucked in. That's just where you would need to be very, very lucky and have something that will give you enough energy to knock you back out.
Yes. And also something at 1.5 Schwarzschild radii is known as the Photon Sphere. And so it's a really cool location outside of the event horizon where if light happens to get caught there, basically the photons of light will spin around in a almost balanced orbit.
Right. It's like an almost perfect circle. So if you were at that's the photon sphere, right?
Mm-hmm. And you put your head there, you would be able to see the back of your head.
Yeah, like the light would just orbit permanently, and you'd be able to see behind you essentially.
I think that, again, as a disclaimer, this is now the part where the quality of our knowledge goes down severely.
Right.
And so
I'm quite confident that that's how this Photon Sphere.
I'm
1.5.
perhaps on this particular thing, but moving on now, this is the kind of stuff that I find
Right.
a lot more confusing. And also, I believe the stuff that has a lot more active research going on as well.
Yeah, we are undergrads, so we don't know all too much, but it's also where the the main field of black hole research is, and that a lot of people are unsure exactly what's going on, because obviously we can't get close enough to even try to look at what's going on.
Like the end of the movie Interstellar, where I have no idea what's going on.
Yeah. Although black holes, there are still things that we know pretty confidently. I think the stuff that's around black holes we understand well, because general relativity tells us very well what's around them. I think it's just within the event horizon, I think that's where we're not really so sure. And this is the other thing that's interesting about black holes, is that they're kind of a test environment for our theories, in that we have, so generally in physics, we have this theory of quantum field theory that explains well how quantum mechanics work and how special relativity work very well together. And so we can explain how very, very small stuff works with a very high degree of precision. We also have this theory of general relativity that tells us how huge objects over huge distances move through space. And this has been the objective of physics for quite a while, to kind of reunite those two theories. And I think black holes are the interesting frontier of where these two theories actually meet, because in general, it's really hard to think about how quantum mechanics works in space in general. But I think when it comes to black holes, this is kind of the best place for us to see where both quantum mechanics and relativity are interacting together at kind of in the same place.
Yeah, because if you can predict, get your theories right at the most extreme environments, the very small scales, the very volatile places, the very large scales, then, you could easily and reasonably extrapolate to say that your theories are going to work for everything in between.
Yeah.
So if we're able to, predict accurately what's happening at black holes, then we'd have a big understanding of what's happening for quantum mechanics just outside, in blank space, and then also on a very small scale as well.
But I mean, with that aside, though, there are still very cool things that we're pretty confident about,
right?
That are going on in black holes, such as, for example, this thing where as you get closer and closer to a black hole, time goes way slower and slower for people observing it. So, for example, if we took a person and chucked them towards a black hole, as that person got closer and closer to the event horizon of the black hole, time would slow down for us. And even if we lasted forever, we would never see that person cross over into the event horizon.
Right.
Which doesn't mean, obviously, that the person doesn't go through, because an object that is accelerating towards the event horizon will go through it.
So in their perspective,
from their perspective, it's just that from our perspective, we will never see that, which is a very cool thing to think about, because it means that there's like two completely separate things that are going on in the universe that seem equally real. And then that brings up this whole idea of what is, seeing or being real and things like that, which is crazy that for someone observing it, nothing goes into the black hole. But then for something that's in the process of going into a black hole, it definitely is, and that's very real.
Right. And this event, or this process, is called time dilation. But that brings up the argument for people here on Earth, we never see them cross. But from the perspective of the person who's crossed, their time continues at the same rate, and therefore the time outside of the black hole has to speed up. So the closer and closer they get to the center of the gravity, the singularity in the black hole, the faster the rest of the universe is going to speed up in their perspective. And so it might be a bright flash for all the light, but they'd be able to see, the end of the universe, theoretically.
Is that true, or is it I'm not sure about. I'm not sure about this.
The person would probably die by the time they get the black hole.
I mean, yeah, okay. Yeah. If you're invincible, though, it's theorized that because from Earth's perspective, they slow down. In their perspective, time has to go the same rate, and therefore everything else has to speed up.
Is that true? Or because, in special relativity, at least what we learned is that, moving is just relative. So if something is moving really fast, it's only moving really fast relative to something. So for example, I throw a rock, the rock might be going really fast away from me. But
Right.
on the other hand, from the rock's perspective, I am moving away from it really fast. So does that mean that when you get close to the event horizon of a black hole, does that mean that, so for us on Earth, if we throw someone near a black hole, time, we never see them get there, and time slows down for us. Yeah. But
Right.
from their perspective, do they then get to see the kind of the universe unravel really fast, or do they have the same thing where they never really see anything changing elsewhere? I don't know.
As far as I know, as long as you don't have a change in direction, then it works that way. But that, that's something that is only theories, and that we'd never be able to prove.
Mm-hmm. Well, I mean, I'm sure theory has a pretty definitive answer.
Right.
The problem that we just posed, I just don't know the answer to it.
Basically.
Yeah.
And then, sorry, there's I know that. So we talked about aliens 1 and 2 weeks ago, and so one of the things that we talked about was the Kardashev scale, which is sort of ranking alien civilizations based on on how much energy they use.
Right.
And one of the proposed ways that a super advanced alien species could generate energies from black holes is through this thing called the Penrose process. And so briefly, it's if you throw a piece of like a machine at a black hole, and when this piece of material reaches the zone around the black hole called the ergosphere, which I believe is at sort of 3 Schwarzschild radii from the center, then if in the ergosphere you can make this object split into 2 even parts, one aimed directly at the center of the black hole, then I think it can then somehow fling so one of the pieces goes in towards the center of the black hole, and I think by the same token, you have the other piece, the remaining piece, that gets flung back at where it came from, with even greater and with very large amount of energy.
You would need a conservation of energy, and because you sent one into a black hole, the other one has even more.
And I think this is this process only works if it's a rotating black hole. Because rotating black holes, I believe, then again, I'm not entirely sure about this, but my understanding is that rotating black holes kind of pull the fabric of space-time around them and kind of spin it as well. And so by using that effect, the Penrose process would be a way of extracting rotational energy from a black hole. So if you could successfully perform the Penrose process, then I believe this is a way of actually reducing the rotational energy of a black hole.
And I should also say that there was at least in physics.org, there's an article published June 23rd of this past year, and a team in University of Glasgow, they published a paper in Nature Physics titled Amplification of Waves from a Rotating Body, where they're able to basically show that this idea is possible.
And experiment. I mean, there's lots of other cool kind of thought of things that are still, I believe, open questions in physics. They might not be, but from my understanding, another big topic of debate, another source of questions in black hole theory is this idea of information loss. So quantum theory as we know it, which is the description of all of the smallest things around us, says that information can never really be lost. So for example, if you take a book and you burn the book, don't burn books, that's not a good thing. But if you did take a book and you burnt the book, you wouldn't really lose the information in the book. It could somehow possibly be rebuilt. Not that it really realistically could be, but still the quantum information of the stuff in the book is not lost if you burn the book.
Right, like you have all the same materials.
Right. However, there is a However, if you throw like a book or some piece of information or some like quantum information at a black hole, then no one really knows what happens to it once it's crossed the event horizon and it goes inside the black hole. And it's this idea that maybe quantum mechanics isn't fully describing what's going on inside a black hole, if indeed the black hole were destroying information, because quantum mechanics tells us that information cannot be destroyed. And from our understanding, maybe black holes do destroy information. And so I think this debate was coined the Hawking Susskind debate. And I believe one of the solution, and so Leonard Susskind, who is a professor, I believe at Stanford, said that this theory that information is lost in black holes leads us to a world of, I believe he used the words quantum madness, and he wanted to save the world from quantum madness by finding a way to explain what happens to information once it crosses, as it's crossing the event horizon. And I believe that his solution was that the information is kind of kept on this 2D surface around on the event horizon of a black hole. And I'm not really sure how this works, because this is starting to get into some really, really complicated stuff.
Right.
But I believe that this information is kind of stored on this 2D mesh of space-time on the event horizon, and which apparently brings up loads of implications, such as the holographic principle, and that everything might just be a projection of way higher dimensions into lower dimensions and things like this. I have no idea what any of that means, but I think it's still cool to think about it.
And I know there's some theories that kind of apply wormholes to black holes. You know, a wormhole has one spot you go in and one spot you go out. So I know people theorize that there's something called a white hole, and like maybe an alternate universe or parallel dimension or something like that.
Or just somewhere else in our own.
Or just in our own that we haven't found. But essentially, all of the material and information that gets sucked into a black hole gets ejected at a white hole. And it's just the opposite of a black hole, essentially.
Yeah. And then, which is really, it's really interesting to see how so many different competing theories are being applied to explain kind of what's going on in the world, using kind of black holes as a test of the theory. So, for example, one of the proposed ways to bring together gravity and general relativity and quantum mechanics has been string theory, and which is this model, I guess, where the universe is just loads of little vibrating strings in lower or higher. I don't know. Are the extra dimensions lower or higher?
11 dimensions, right?
Right. Either way, I don't know if the 11 are higher or lower dimensions, but nonetheless, it's a model that explains the universe in vibrating strings across in the universe. But there's lots of models like loop quantum gravity and things like that, which are still being put forward, and none of which have been conclusively either ruled as correct or incorrect. And I think that brings us on to kind of the last point, where at least one of the most interesting points for me is the universe is kind of what, maybe we can just explain the universe by how we want it to be explained. So I believe that, I can't think of a good reason why the universe would be little strings as opposed to anything else.
Right.
You know, for me at least, there's no motivation for a string as opposed to any other shape or things like that. And I think that's the cool thing about physics, is that we can use all of these principles to come up with really, really good theories about why things happen. But then we still realize that we don't know why. So, for example, Newton came up with gravity, and he very successfully explained why the planets were moving around the sun. But then, and some people might say, "Oh, that's game over. We know physics." But then Newton was able to recognize that even though he can explain how the planets move around the sun, he can't explain why they're moving around the sun. And so I think that's a really cool thing of physics that gets illustrated well in black holes.
And I think even with the ideas of unifying quantum mechanics and general relativity, it's often quoted as the theory of everything. But I think
Mhm.
even that understanding won't be the quote unquote theory of everything. If there's one thing science has
Right.
shown us, it's that there's always progress to be made and
Mhm.
questions to be asked about what we
Yeah,
know.
like with the creation of the string theory, um, I know there was a research article that came out January 2020 that essentially used lasers to confirm that there was a fourth dimension of space. So normally people think of 1D, 2D, 3D, and then like time as the fourth dimension.
Mhm.
But these researchers, I think it was in the journal Nature Journal, this January, they essentially said that as a parallel of like how 3D objects make a 2D shadow, 4D objects can make a 3D shadow, and they were able to like prove that the fourth dimension existed.
Well,
And
isn't
it's
yeah.
just it
Oh
shows how
wow.
it shows how like we could maybe talk about it in a future episode, but it shows how the string theory and black hole theories and how to explain these things help drive other research that are proving these crazy things and
Or
helping unravel
or
the
all of
secrets of
this
the
might
universe.
just be a fruitless exercise and we're just wasting our time.
That's true. So it should be,
True.
again, noted that we are undergraduates. We don't have a full understanding of black holes. But one thing we did discuss when we were planning this episode is that there's tons of researchers at the University of Michigan and the departments of physics and astronomy that research black holes. And so we think it'd be interesting in the coming months to bring one of them on as we have previous professors and, ask the experts as to these odd questions we have and have somewhat answered.
Cool. As always, please like and subscribe.
Oh, yeah.
We appreciate it very much.